Hello, everybody. Can you hear me? Yeah. Okay, thanks. Thanks a lot for joining. So let's wait 1 minute in order to start at 10. Okay, I think it's time to start. So I see there are several people joining in the chat room. So hello, everybody. My name is Luca Marcella, and I work at CSCS in the User Engagement and Support Unit. And we are here to present the webinar on best practices for building software on Piz Daint. As I anticipated in my email sent to Piz Daint users, we will address a brief description of the Piz Daint system, and we will focus on how to build your code, especially stressing the EasyBuild framework that we have recently adopted at CSCS, so how to best use it. In this webinar, we give space for questions as usual in the chat room. So you cannot talk, but you can write in the chat if you have questions while I'm discussing the slides. In order to help me replying to questions, there are some of my colleagues here with me, so they can address your questions during the webinar. I'm also recording the webinar, and I have shared already in the collaboration view the PDF of the slides. So I hope that you can download the file. Otherwise, I will make anyway we will make the slides available also after the webinar. So the recording will be available on the CSCS page under the tutorial section, and the PDF slides will be available as well. So let's start then with the webinar. As I said, the webinar is focusing on the best practices for building software on Piz Daint. We will start then with a brief description of the Piz Daint system, the Cray XC50, which is still a hybrid system featuring also an XC40 set of nodes. We will describe briefly the features of the hybrid system, which you might already know, but just to recap what we have on the system. Brief description of the operating system that is currently the CLE 6.0 just for the sake of knowing where we start from. Then a quick recap of the Nvidia CUDA Toolkit version that we have on the system, and some links, useful links for developers and people building CUDA code. And then we go to the section, most important section of the Cray programming environment, so the Cray PE of August 2017 that is currently available on the Piz Daint system, some features of static versus dynamic linking, and the main focus of the webinar, so the EasyBuild framework that we have adopted at CSCS. So let's start with the brief description of Piz Daint Cray XC50. These are the system specifications of our flagship computing system, Piz Daint. So the model name of Piz Daint is Cray XC50. Still, as I said, it's still featuring XC40 nodes. So the XC50 compute nodes are equipped with Intel Haswell processors. You have on the right side of the slide the technical description of the name of the Intel Haswell. And the Haswell nodes feature an Intel Haswell processor with 12 cores and 64 gigabytes of RAM. Each node comes also equipped with an Nvidia Tesla GPU, a P100 called Pascal GPU, with 16 gigabytes of RAM. The XC40 nodes, Intel Broadwell processor nodes, they feature 18 cores per processor, and nodes that can have a memory ranging from 64 up to fat memory nodes with 128 gigabytes of RAM. The login nodes are slightly different. So when you build your software, it is somehow important to remember that you have the correct programming environment, which we will describe a bit later, in order to target the correct architecture for which you want to build your software. The interconnect of the system is an ARIS routing communication, ASIC, with Dragonfly network topology. And then one of the features that are important when you run your code, the scratch capacity, which is on Piz Daint 6.2 petabytes. It has been improved at the last upgrade. One important note about the scratch file system. We have recently updated the Sonexion 3000. You might have realized in the past there have been few interventions, and we are confident now that the performance has improved. However, please remember that the Luster file system, the Sonexion 3000, is targeting, in general, is optimized for large I/O and not for I/O small files or many files, let's say, many small files. So please take this in mind when you plan your simulations. Another important information about the other file system, which we will see in the next slide, is that you have, in general, a project or a store folder if you have a contract, a project if you have a production project. These folders are not accessible by Piz Daint compute nodes, something that you have to take in mind when planning your simulations as well. So let's see now the file systems available on the system here that are relevant also when you build your code, because you have to target a correct file system to keep your important files. So as you see, on Piz Daint, so the main system here on the left, we have a scratch that is a Luster file system with a soft quota of 1 million files in place. What does it mean? You have it here in the node, soft quotas. So the scratch space on Sonexion 3000 for each user, the variable $scratch points to the folder scratch Sonexion 3000 $user, your username, has a soft quota set to prevent an excessive load on the system. So users exceeding the soft quota of 1 million files will be warned when they submit a job, and the job is submitted when you have already overcome the quota. At that point, you will not be able to submit new jobs. Please remember that you can always check your quota with a common quota on ELA, the front-end system. So please make sure that you don't overcome this quota. Please also remember that there is an expiration date of your data on Scratch, so the files will be erased by a script, clean script every 30 days. So files older than 30 days will be deleted. So this is not the right file system to address for keeping your important data, of course, but you need to copy them and move them either to your long-term storage location at CSCS. This might be project, or this might be store if you have a specific contract. And you can also use your home if you fit the sites available on home. In particular, on home, here it's under the /users file system, which is a GPFS file system type. You have a maximum of 10 gigabytes per user, or 100,000 files that you can keep. So keep it also in mind, because in general, people build software on the home folder. This is fine up to this point. If you need if you have larger space needs, so for building big software projects, for instance, that could not fit home, then please go to your $project folder instead. So the $project variable points to your project folder and under the /project file system. The project file system in general gives you an amount of space that is shared with your group that can vary. So in general, is of the order of few terabytes. And you have, in general, a maximum limit of 50,000 files per terabyte. So it's quite large. And it's usually kept up to the end of the project. So keep also that in mind, that you need to move your data when your project expires. It's backed up, and the backup covers the past 90 days. And it's a bit slower, of course, with respect to the Scratch file system, but it has the advantage that you can keep for long-term your data there. So that means that you can actually keep your files in project, move them to Scratch when you need them for your simulations, together with executables, libraries, and datasets. And for that, you can use the xfer transfer queue that is available on Piz Daint. The xfer transfer queue is explicitly meant to move data back and forth from the project file system to the Scratch file system for your simulations. So let's go now to the operating system that is available on the Piz Daint supercomputing system, that is a Cray Linux environment, version 6.0, up04. The Cray Linux environment, CLE, is the usual operating systems on Cray supercomputers. In our specific case, at the last upgrade, we upgraded to version up04 of version 6.0. And this version is based on the novel /12 SP2 operating system. So keep that in mind in case you need to build your software, so you know from which operating system you are starting from. Then the software release available on Cray XC50, as I mentioned, the up04, comes with a set of features that are described in the link that is available on this page. The link points you to the Cray Publications portal, and probably it's better that I open that. No, maybe, yeah. So, okay, I think I will put it in the notes, because actually I'll put it later, the link to Cray Pubs, that is the main portal for the documentation. Since I shared the PDF slides, if in case the link does not work, I will make it available in the chat room. This is an advanced guide, so you might not really need that, but in case you are curious, you might have a look. Let's go now on. Okay, that's the link about the Cray documentation, which I mentioned before. So Cray Pubs, it's the main Cray documentation portal. So you can search for Cray books, man pages, third-party documentation there. You have both HTML and PDF. It's quite useful in general. You have also some information in the man pages on the system. So if you type the Linux man command, followed by the command you're interested in, or the module that you want to check, then also man gives you some information. Let's go now to the Nvidia CUDA toolkit. So the Nvidia CUDA toolkit that we have on the system is currently version 8.0, which features a comprehensive development environment to build GPU-accelerated applications. So it includes, for NVIDIA GPUs, the math libraries and the tools needed for debugging and optimizing and profiling your application performance. It comes with programming guides, user manuals, so API reference and online documentation. So, if you develop CUDA code, you can actually benefit of the link to the NVIDIA developer portal, which is developer.nvidia.com, CUDA zone, which is quite helpful in general. So in terms of highlights in CUDA Toolkit version 8, in general CUDA, you should remember that we have on the system Piz Daint Tesla P100 GPUs, so Pascal GPUs, and you need to target this architecture with the NVCC flag SM_60. So NVCC is the Nvidia compiler for CUDA code. If you load the module CRE Axel Nvidia 60, then the module sets the environment to target the builds on the Pascal GPU. The CUDA now had support for some additional features with respect to previous versions, like GPU Direct Async, which improves application throughput on the GPUs. And you have also CUDA tools like CUDA compilers that supports now Intel C++ version 16, and the CUDA profiler that can now profile also the CPU to identify hotspot regions in the code. So CUDA libraries, it's important to remember that with version 8.0, there is now a built-in for FP64 atomic add, so you cannot override this definition with the custom user function that had some impacts. For instance, when we try to install some applications, let's say CP2K or VASP to mention two, that were redefining the atomic add with a custom function, and that was needed to be worked around. For complete features and release notes of the CUDA Toolkit version 8, please refer to the official documentation on the links below on the Nvidia dev blogs, Nvidia documentation portal, docs.nvidia.com, and developer.nvidia.com as usual. Again, here remember the important links to the Nvidia documentation portal and the CUDA Toolkit for developers. On our system, you can get some information on the CUDA Toolkit and the CUDA installation with module help CUDA Toolkit, and specific information on the Nvidia compiler with nvcc-help or the CUDA debugger CUDA gdb-help. Please let me remind that we have a DDT debugger in place on the system that also allows GPU debugging on the GPU. So the DDT debugger will still be our flagship debugger system, software, sorry. Let's now switch to the main topics of the webinar, that is the Cray programming environment and how to build your software on the Cray XC50. So the Cray programming environment on the hybrid Piz Daint is usually released by Cray on a monthly basis. Excuse me, the PDF will be available after the session. Excuse me for the interruption. So the programming environment is released on a monthly basis by Cray in general, not every month, but usually it does. And it's not, although made default on a monthly basis on the Piz Daint system, because we need, let's say, thorough testing. So we keep, let's say, changing the programming environment twice per year for the moment, the default one. We might install new programming environments without making them default on the system. The environment contains the set of libraries that you need to use each compiler. So I show you here a screenshot of the Cray programming environment, program Cray, which is the default. And the default programming environment comes with a set of module files that you can see in the list. Among them, you will see the Cray mpitch, the MPI library. Maybe I can highlight that. Yeah, so you can find that here, with program Cray mpitch version 7.0, 7.6.0. And then the default target architecture will be the Cray PE Haswell. So it's targeting the GPU nodes if you build immediately with the programming environment as it is. Of course, users can change the target architecture by loading one of the following modules that we provide on the system. So one is called Daint-GPU, and it targets the XC50 architecture. So Intel Haswell and P100 Tesla GPUs. although the CRAE-PE as well is the default. If you load Daint GPU, you will have additional software available for the GPU portion of the system. The Daint-MC module will target instead the XC40 architecture, so the Intel Broadwell multi-core portion of the system. The modules above will update your module path. So module path is an environment variable that is present in your login session that holds the path that is checked automatically to find new modules. You can use the module switch command in the system in order to change the environment. Now, let's see a brief description of what the CRAE-XC programming environment features. So the CRAE-XC PE1708, it is currently the default on the system, includes the CRAE Developer Toolkit. So it's a module called CDT, and the version is 1708 as the name of the programming environment. Non-default programming environments can be accessed using the CRAE Development Toolkit module CDT. In fact, this module comes with the possibility to change the defaults and revert back to a previous version of a programming environment. Now, available on the system, you have 3 CDT modules, if I remember correctly. So you have the former 2016 November PE, the current one, and I think a new one, a slightly more recent new one. So if you use that module, please keep in mind that you are changing the whole programming environment and reverting back to a different PE. Now, the current PE also came with some new software. So the CRAE compiler environment, featuring the CRAE compiler, version 8.6.1, CRAE debugging support tools, some new CRAE performance measurement tools, perf tools, version 6.5.1, that you might have used if you have submitted your technical report for the proposal submission, together with other compilers as well, because the environment also featured GCC version 7.1.0, which is not the default, because the default is still GCC 5.3.0, but this comes as a more recent version that you can also switch to if you wish. So let's now talk about static versus dynamic linking. Now, you might already know that, but it's always better to stress it. Binaries can usually be linked statically and dynamically to the libraries that are used in your executable. Now, CRAE compiler wrappers are scripts that allow you to reduce the amount of information that you have to pass to the compiler. These are named CC, capital letter CC and FTN, depending on the compiler that you address. That is main C, C++, and Fortran. By default, these wrappers, these scripts, they create a statically linked executable on the system. If you want to change this feature, they allow you to specify a dynamic linking flag that is -dynamic. Alternatively, you can also export an environment variable, excuse me, that is CRAE-PE link type, setting that to dynamic before building. In that case, the linking will be dynamic. However, please note that if you load the CUDA Toolkit module or the CRAE-PE Axel Nvidia 16 module file, then automatically the system changes the linking to dynamic. So it defines the CRAE-PE link type variable as dynamic when you build CUDA code by default. Now, what is the advantage of a dynamically linked executable? In general, the binaries can be used after a system library update. So if the names of the libraries do not change, then your executable will find the new ones. With statically linked binaries instead, where you have all your libraries inside your executable, then if they use directly or also indirectly the network interface, they must be recompiled. For instance, using the UGNI, so the network interface, and the DMAP library, for instance, for improved and optimized collective in the message passing framework like MPI. These kind of situations requires a recompilation of your code anytime there is an update and we change for the underlying libraries with which you built previously your executable. This includes also applications using SHMEM libraries, not only MPI, as well as the partition global address space of Fortran with core arrays, UPC, and Chapel. Please keep in mind that in general there is no backward or forward compatibility provided by Cray with DMAP and UGNI libraries. So let's see a practical example of how to build a static binary linked to the MPI library on the system using the compiler wrapper CC for C code and the default program Cray, the Cray programming environment that you find as soon as you log in on the system. So the Cray wrapper flag dash help shows you all the available flags of the compiler wrapper. So CC dash help on your prompt, on your shell prompt, will give you all the options. In this small example, I use the flag dash crayp verbose, dash verbose, that gives you a verbose output that shows you what exactly the wrapper script is putting on the command line. In general, this is hidden. So in this case, you can see that in the example on the right, that typing cc crayp verbose mpi.c, a simple MPI code. I then get this long command line, which features a lot of include paths and library paths as well. It does linking in the same stage. So if I check afterwards with the command ldd, my executable mpi.x here, I get a reply, not a dynamic executable. In fact, no CUDA module is loaded in this example. Hence, the MPI library is linked statically by the Cray wrapper. We can check that also looking at the size of the executable, which is listed on the right side at the bottom. So the size is almost 10 megabytes for a small MPI executable that just does a simple communication of a hello world. So you see that the size is relevant for a small executable because it includes a lot of libraries. Now, if you want to be sure that your routines have been included, you can use the nm command, which lists the symbols from the object files. So if I type nm mpi.x and I grep for the function that I want to check, like mpi_send, the MPI send routine, well, you can find it in the object file, in the executable. So it means it has been included. Let's now see, on the other hand, how it works if you link dynamically. So we have again the same example as before. So the small MPI code, which now features also the possibility to use the GPU, passing some arrays to the GPU and getting it back. So I have a CUDA portion of my code. So I have a file CUDA.c, and my main is still mpi.c. So first thing, in order to compile CUDA code, you need the CUDA compiler, the Nvidia compiler NVCC. NVCC flags can be retrieved with the -h or --help option. In this example, I only use -arc equals sm_60. As I mentioned before, this will target a build for the Pascal GPU, the P100 that we have on the Piz Daint Haswell nodes. Now, as you see, as in the right side, as soon as I load the module CUDA Toolkit, then the variable crayp link type gets defined and gets defined as dynamic. This will mean that even if we will use Cray wrappers, your binaries will be linked dynamically to the libraries on the system. So let's see the example here. I compiled the CUDA code with NVCC using the flag -arc equals sm_60. Then I build the main in the verbose fashion as before. Now, since I use the -c compile only, you see only the include paths and not the link paths. And then here below, I link the two objects with the wrapper CC, which will link then dynamically all the other libraries in the system for which you see the includes here. So if I now use the ldd command that prints the shared object dependencies, and I grep for the MPI library, for instance, now you see that the MPI library is no more in the executable, but it is linked dynamically to a certain location in the system that is pointing to libmph cray SO. So you have the full path here. So since the MPI library is loaded, you see that. If the MPI library is not loaded and the path is not available, you would see missing path. Then you can load the module file just to check that the MPI library is correctly defined and it can be found in the system. The main difference that you can immediately see looking at the size of your executable, if you look at the bottom of the slide on the right, then you see that now our executable is, here the size is in bytes, around 16 kilobytes, because all these MPI communication libraries and of course the CUDA libraries are linked dynamically. That's the most evident difference, but of course, as I mentioned before, the important difference is also that if you have an update of the system and the library names are not changed, then your executable might still work, provided that the routines that you use are still found in the libraries in the new versions. So let's see now another important topic that I mentioned before, the non-default programming environments that you can address with Create Development Toolkits. Here you have seen two simple examples of how to build your code using default modules on the system. So suppose that you want to revert back to a module that is no more default. And that module might come with other modules dependent on the first one that are not defaults anymore in the Create programming environment. The correct way to address this issue is using the Create Development Toolkit module files, the CDT ones that I mentioned briefly before, which you can see with the command module avail CDT on the system. As far as I remember, there are 3 CDT modules now on the system. The current one, one previous one, and more recent one. So when you load a non-default CDT module, the default one, of course, addresses the current programming environment, which, of course, you don't need to change if you are willing to use the current defaults. If you change the CDT module, defaults will be changed. And at the moment, you need also to update the libraries that will be the new defaults that are required to build your software. This means that you need to prepend the environment variable cray LD library path to the generic variable LD library path. This is a step, unfortunately, still required because as soon as you update modules in the Cray programming environment, the variable cray LD library path gets updated with every product library that is loaded in the current environment. Or if you unload any module file, cray LD library path then will remove the corresponding path. But LD library path, which is the one that in general you need at building or at runtime when you have dynamic linked binaries, needs to be updated by hand. So let's give a concrete example. In the example, the short example below in the shell emulator, I want to use the Cray development toolkit dating back November 2016, which is still available on the system. Then I module load CDT 16.11. This operation will revert the defaults to the situation of the PE of November 2016. That means that I have now, for instance, a Cray netcdf library that is no more the current default, but is dating back to that date. And then I have to update also the LD library path, taking that into account, which I do by exporting LD library path equals to the $cray LD library path variable, and then I append with a colon $LD library path the current content of LD library path. That ensures that everything I will build now will search for linking paths in the Cray LD library path before, and then the rest. So I'm pretty sure that I'm updated now correctly my current environment with the defaults that have been dated back to the 2016 November PE release. You can find more information on the user portal at the link provided below. So under the main section of the user portal, user.cscs.ch, called Scientific Computing, you find a link called Code Compilation that has several examples. The current default modules for compilers, libraries, and tools, the main ones, are listed in this slide. So if you need to address anything that is older and is still available with the older Cray CDT, you can use the procedure that I have outlined so far, reverting back to a previous CDT. Otherwise, you will have these modules loaded when you have a current programming environment on the system. Here you have compilers for Cray, GNU, Intel, PGI, communication libraries, the MPI and shell memory, numerical libraries, Cray libsci, which comes with a lot of scientific libraries, including linear algebra libraries like BLAS, LAPACK, routines. Cray FFTW is the module name for the fast Fourier transforms. Cray TPSL is the third-part scientific library module files that includes several scientific libraries. You can check them with module help Cray TPSL. Cray Trilinus addresses the Trilinus library. Then we have performance tools. Now we have the current default perf tools 6.5.1 that you might have used already. I/O libraries like Cray HDF5, serial and parallel, and NetCDF interface to Cray HDF5 parallel as well. Debuggers, as I mentioned before, DDT version 18 now on the system after you load Daint GPU is the main the main debug software that we have on the system. And then also pre- and post-processing modules that came with a recent programming environment released by Cray, like Cray Python and Cray R, which are still in a, let's say, development state. Therefore, we currently provide additionally, if you load Daint GPU, a extension module file, which includes packages that are not addressed by the default Cray Python and Cray R modules. Now, here I list briefly some defaults that are available for scientific applications and libraries on both Daint GPU and Daint MC software stacks. That is the defaults that you would see in case you load one or another GPU or MC module file. As you see, the versions here have been updated recently. Sometimes there might be a newer release of the application, although we don't make it default immediately. And in the slides that will follow, I will show you how you can actually build locally a new version of these applications that we provide in case we don't make the newer one default yet. So let's switch then to EasyBuild, the installation framework that we have used at CSCS. Okay, before switching to the topic, if you have more questions on the topics that we have discussed so far, please just use the chat room. But I think that you're already using that, so please just go on. Now, EasyBuild is an HPC software installation framework that has been developed by the University of Ghent in Belgium. So what are the advantages and the main features? Now, it fully automates software builds. So it allows you to reproduce a previous build seamlessly. So it addresses all the standard ways of building the code. For instance, the configure, make install procedure. Much more than that, it addresses also CMake builds and so on. Software recipes, so let's say configuration files for building software, are made simple. And the important feature they have, they can build with automatic dependency resolution, provided that you provide the dependencies and that you have the dependencies installed, let's say, or they can be downloaded anyway. We'll see that later. The key features are the possibility to build several versions, several builds, with installation prefixes that might be dedicated, and creating immediately the module files, so you can also build yourself your own module files, not only use the ones that we provide. You can share your recipes, your configuration files with the HPC community, and one of the main advantages I see in EasyBuild is in fact the growing community that uses that, so the possibility to have immediately new recipes for building software as soon as the software comes out. It also allows for patching, so you can generate a module file with a patch version of the code, and you can have the logs of your build, so you can check the build also at a later stage. Some advanced features are also the possibility to archive your recipe files that we usually call an easyconfig file. So that's the configuration file used by EasyBuild to build your software, and can be archived locally and also in an online repository. We use, for instance, at CSCS, the GitHub repository, which is also the main repository used by the main EasyBuild developers. You can build also an entire software stack with just a single command using the dependency resolution flag -r, which stands for --robot, and this can be done in parallel, so to speed up the building. Last but not least, there is a very robust testing phase before you have these recipes released. So unit tests are fully run before each release of EasyBuild. For more information, please refer to the main EasyBuild documentation portal available on easybuild.readthedocs.io. Let's go on and see how do we implement the EasyBuild framework at CSCS. Now, EasyBuild is available through a module called EasyBuild-Custom. Now, this module defines several locations, several paths in the files, in the system, where you can find configuration files that we have already provided, and will allow you to build and install modules in the current software stack. So in order to load this module on Piz Daint, though, you need to load before the module corresponding to the software stack that you intend to address. So either Daint GPU or Daint NC. So on the Cray XC50, that is the standard procedure. You won't find the module EasyBuildCustom unless you already define a module Daint GPU or Daint NC, because that first module load defines the target architecture, which is essential before building your code. So you will see that after loading the Daint GPU module and EasyBuildCustom module in this example, you will find in your environment several variables, new variables that feature the EasyBuild name, and some of them will point to this location. Specifically, the variable called EasyBuild prefix will point to your home, EasyBuild, Daint, and then Haswell or Broadwell, depending if you have loaded a Daint GPU for Haswell or Daint MC for Broadwell. This is the standard, the default prefix folder where everything will be installed in this session. In order to use this installation folder with your builds also at a later stage in a new login session, without loading again the module EasyBuild, you can just prepend this path, so home, EasyBuild, Daint, Haswell or Broadwell, modules all, to your module path. Module path is still the variable that holds all the paths that are checked by the module command once you want to see the modules available on the system. You can also override these default installation folders, or also the default CSCS repository folder, exporting the corresponding variables that are listed here before loading the module EasyBuild. Last but not least, the important command in order to build all your software is EB, that stands for EasyBuild, name of your EasyBuild configuration file that always ends with the extension .eb, and -r stands for --robot to recursively solve the dependencies. We'll see that the examples will feature this command line often. So let's see what happens then when you load the module EasyBuild on the system. Now, as soon as you load the module Daint GPU and EasyBuildCustom, as you see in the slide in the shell emulator on the right side, the environment variable Cray CPU target gets defined to match the architecture that you have selected. So in this case, Cray CPU target is Haswell, because you have loaded Daint GPU. Now, if you use the command EB, you can have also here an help screen that comes with -h, lowercase, or capital H, capital H, to have a longer help screen, a more detailed one. In particular, now we will use an option that is listed also in the help screen, that is -- show config, that shows you the main configuration of the EasyBuild engine. So this is the default configuration in the system. And as you see in the list of the paths that are defined, there is the prefix path that points, it's listed here, prefix. I hope you see the pointer. Prefix, well, I can also highlight that anyway. Highlighter. So the prefix on the highlighter doesn't go very. So the prefix path is pointing to my home directory, EasyBuild Daint as well, because we have selected the Daint GPU module file and loaded that. Other important paths are the robot path that is looking for automatic resolution of dependencies, and the source path for the sources. So in this session, actually, everything you will build will be built under the EasyBuild prefix that it is defined by default. You can still change it by exporting another EasyBuild prefix name before loading the module EasyBuild. Let's see a simple example. So we want to look for some software if CSCS has provided, let's say, a configuration file for GROMACS, the GROMACS molecular dynamics engine. And we want to filter our search to get create tool chains. So you see on the right side with the shell emulator, the command eb-S. Capital S is the search flag. And we look for GROMACS and we want a recent version, let's say 2016. Then we grep for Cray, because the software that we provide on Piz Daint comes in the name with the Cray keyword. So you see now in the output several matching items. In particular, we want to build something that is not yet available on the system. You see there is a Cray GNU 1708 Plume D230 with CUDA 8. So what should we do in order to build this locally? We use the eb command. We use just the name of the recipe with the .eb extension, and we use the -r flag in order to resolve dependencies automatically. Then the build will start in your shell, informing you of the steps going on. You can always check the log file while building. In case of crash, it is useful to spot mistakes. And after the build, the make and install procedure, sanity check is performed as well. You will see the location of the build. At the bottom, results of the build can be found in the log file. And the log file is located actually where the builds takes place. So under my home folder, EasyBuild Daint as well. Here, the software folder points to the actual location where the executable are stored. But then there will be also a modules folder, which you will need to add to the module path if you want to use this module later, with the command module use and your local path. So you will see that in the following examples. What about changing a bit the build? Let's say now we have just installed a module, but a module that was corresponding to a recipe that is already provided. Suppose now that you want to try to install a more recent version of the software that is not yet provided in a recipe that you can find on Piz Daint. Now, EasyBuild comes with a nice feature that is called tweaking an existing EasyConfig file, and an option beginning with --try, which allows you to try a new software version or also a new tool chain. And if the EasyConfig file, so the recipe file, allows that, it can solve and update the dependencies automatically. Let's see that with the previous recipe. In the previous slide, we have seen that CSCS provides a recipe for GROMACS 2016.3 featuring CUDA 8. Now, we want to try if this recipe can work and install a the most recent version of Gromax, 2018. Then we do that. We use the flag --try-software-version equals 2018. This might correspond to the version of the software that you want to address. And -r as usual to resolve dependencies. Now the build would start. As you see, EasyBuild will process a so-called tweaked easyconfig file. So it automatically changes the recipe, writes in the temporary folder where you build the new tweaked recipe, and we'll start building the software Gromax 2018 with the rest unchanged. So it's still Craig GNU 1708, the programming environment that is the default, and CUDA 8. And it's apparently successful because it completes and it writes in the EasyBuild prefix that I have selected. So in this case, it worked because the recipe that we provide doesn't use hard-coded versions, but use string templates. You can check the string templates available in EasyBuild using the flag --avail easyconfig templates with the EB files. And more details can be found on read the docs. So let's go now to an advanced way of dealing with EasyBuild in case you want to customize an existing recipe. Until now, we have used something already provided by CSCS staff, or we have tweaked a bit with a flag of EasyBuild, checking if a new release could be addressed by the same configuration file. But you can also edit your own files. In order to do that, the first step is to download, to clone our production repository on the GitHub and create your own one locally in your folders. You do that with the git clone command, git clone, and then the link to our repository. On the github.com, we have the ETH CSCS project, which features several repositories. In particular, in this case, we address the production repository. Now, as you see, as soon as you execute the git clone command, you might be already familiar with that probably, it creates a new folder called production, and there you will find listed in alphabetical order the recipes that we have already prepared. So you will find then under the production folder, you have an EasyBuild folder, which is the main one that you need. And then under that, you will find a folder called EasyConfigs. There you have a list, alphabetical order of the software that we actually address. Now, in order to use your custom repository, once you have cloned our repository, you need to export the variable eb_custom_repository to point to your local path, production/EasyBuild. And then you load the modules Daint GPU and EasyBuildCustom to address a build on the Haswell nodes. Let's see how then you can edit your recipes. Now, I have already mentioned some features of these EasyBuild configuration files that we call EasyConfigs. These are plain text files that in Python syntax. They define some EasyConfig parameters, so mostly in key value assignments. And they follow a strict naming scheme. So the name is the name of the software. The version is the version that you're addressing. And then there are optional elements in the name, like the tool chain and the version suffix. So the tool chain on Piz Daint is always matching the Cray keyword. And then it might be Cray GNU, 1708 is the version of the chain, the tool chain that corresponds to the programming environment. It might be Cray Intel for the Intel programming environment. The optional version suffix, that's a label that could contain CUDA, for instance, or Python version. So for some builds we need CUDA, for other builds we need Python. Then we might actually highlight that in the name of the recipe so that you know which version are we using. CUDA 8, Python 3, Python 2, and so on. The file name is important for automatic dependency resolution using the -r-robot flag. By default, EasyBuild addresses the same toolchain. So if you have a Gromax recipe for Cray GNU 1708, and then you have a dependency FFTW, for instance, Cray FFTW, then that would be an external dependency. But if it was not, so if it was something you built, EasyBuild would look automatically for the same name pattern, so Cray GNU 1708. Additional parameters that you can put in your EasyConfig file can be looked at with the -a or --avail EasyConfig parameters flag. This by default shows you the parameters available when you use a configure make procedure of building. The procedure is called also a block in EasyBuild, in the EasyBuild framework, and you can change the procedure using the -e option to see which parameters are available in different procedures. In general, what we put in a recipe by default, and these are compulsory, are the name of the software, the version, then the home page and a short description of the software for metadata that will be used by the module help command. The tool chain as well is compulsory because you need to address a specific compiler that is included in a tool chain, like create GNU tool chain will address the GNU compiler based on the programming environment GNU featured by the Piz Daint system. Sources in the sense of file names, so the source that you really need to build, and the source URLs in case you want to download the source code. These are needed as well. You can also put a patches variable to put a file name, a patch file name to patch your code before building. Then very important dependencies. These are the variable that contains the runtime dependencies, and build dependencies, which contains the dependencies that are loaded only at build time but will not be needed when you run. In both cases, you need to define this variable when using the -r, so the automatic dependency resolution flag, in order to find these dependencies. There is the possibility to provide configure options, make options, install options, using the variable config ops, build ops, and install ops. And EasyBuild comes with more variables like pre-config ops for something that you can specify before the actual command .configure. Pre-build ops is in the same way, featuring the possibility to add also options before starting the make, so the build process. Same for install ops and pre-install ops. There is also the possibility to add sanity check paths as a variable. So you had some files or directory names that should be included in the installation folder, and EasyBuild will then, after the installation, check that these files and folders are there. And sanity check commands, simple one-line commands that you can put in order to check if your build has been done correctly. Now, all this happens with an EasyConfig recipe that it's based on what I called a block, so an EasyBlock file that is a Python script, and the default is the configure make one when you type eb-a, but you can change that. In most cases, we use the so-called generic blocks, so something that is a configure make procedure or a cmake build. You have other possibilities, and you can list them with eb-list-easyblocks. And for more details, please have a look at the link below on the EasyBuild main documentation portal. So this includes several tips for writing EasyConfigs. Let's see a specific example, again, with the Gromax software. Now, suppose that you are not satisfied with the Gromax version available on the system because you need to edit some source files, some .c files in the code. Then what would you do? You download the standard version of Gromax, you edit your file, you repackage it, and then you want to build it. Now you can change the existing recipe that we provide for Gromax, that is shown here on the right side of the slide. And you can change the version. So I edited a Gromax 2018 package, repackaged that with some changes in the source code, and then I renamed the version as custom. The rest is not changed, but one single variable, that is the sources. Because now I cannot use the standard source, so I cannot download from the Gromax document, the download page. So I use my repackaged source, which I have to list with the absolute path on the system. So in my case, I put it in my home. And then I have repackaged that as a .tar.gz tarball. Now, please note that EasyBuild expects a build folder that is called after your name and version. So in this case, it will expect a Gromax-custom folder once you unpackage the tarball. So please make sure that you package your tarball accordingly. We keep the dependencies as they used to be. In this case, they are only build dependencies. We don't need at runtime these dependencies like CMake, FFTW, and so on, because the system will find that these dependencies at runtime. And then we start the build. So we can proceed building in the usual way. You see on top, I use the EB command with my Gromax custom recipe now. So Gromax is the name of the software, custom is the version name. And then I don't use the -r here because actually I've built previously Gromax, so I'm pretty sure that I have already all the dependencies that have been built in my own module path. If you have not done that, you need to still use the -r, the automatic dependency resolution flag. Now you see the builds complete, and if I type after the successful build a module avail command, I see now I'm still in the Daint GPU software stack. I see the default Gromax 2016.3 provided by CSCS staff that comes as a default module for Gromax. So if I type module load Gromax without any version, this will be loaded. But I also see in my home space a Gromax custom module file that is provided now by EasyBuild locally with my last build. So as usual, now I see that because I have the EasyBuild module file loaded. If I log in later in a new session, I will need to do the module use local path command in order to add my local installation path. And your local installation path, you see that here. It's my home, EasyBuild, Daint, Haswell, modules, all. This is the standard location where EasyBuild writes if you don't change it manually. If you change it manually, use module use local path to add your local modules to your module path so that you will be able to use them in a next session. So that's it for EasyBuild. And I want just to recap quickly the documentation pages that we generally use. So either craypubs, the man command, the module help. For instance, module help CCE gives you a short help on the Cray compiler environment. But you can also refer for quick and basic instructions to the CSCS user portal, user.cscs.ch. Under the section Scientific Computing, please have a look at code compilation for some instructions on how to build code. And of course, you can always contact us directly with the help at CSCS in order to have specific answers to your questions. So I think I will close the webinar here. We are already at 1 hour, and I thank you for your kind attention. We can leave some more time for questions in case you have questions. I've seen that there have been many. I just want to conclude saying that the slides will be available and the recording as well on the main CSCS webpage under the tutorials link. But now I have uploaded here the PDF version of the slides, which I hope you can see, the .pdf. Are you able to get that? I hope you are, because anyway, we will circulate probably that as well in the user portal. We will put a news with a link to the PDF until we don't publish the recording. So that might be useful as well. And so let's wait for a few more questions. But remember, you will be still able to contact us for specific needs that you might have through the usual channel help@cscs.ch. I think I will stop the recording now.